Hello everyone, welcome back to Power System, class number 9. Today we're going to talk about transmission line parameters, basically resistance and inductance. So let's talk about transmission line first. Transmission line in transmission system of the power system, it has three phases like over here. Each of them are one phase actually. I have multiple conductor in one phase. So you have phase A, phase B, phase C, and this one has two circuits. So this is a two different transmission line here. This one has three phase also. This one has three phase, and each of them has phase has two conductors. So this one is multi-circuit, actually double circuit. This one is double circuit over here. And this is a single circuit transmission line. Right? So transmission line in physically you can see that there are different kinds over here. Especially for this one over here, you can see that each of the phase has 6 conductors. That means it's going to carry a lot of current through them at higher voltage. And this one has single conductor per phase, but it's two circuits. The one circuit here, one circuit here. So this one is 230 kilovolts. This one is 765 kilovolts. That's the highest voltage we have in this country. And this one is 1000 kilovolts. So we don't have any 1000 kilovolts line in the USA, but China or Brazil, they have them. They have 8 conductor per phase. There are 8 conductors there per phase. So we're going to discuss how to find the resistance, inductance, and capacitance of the line, single conductor or double conductor or 8 conductor per phase or single circuit or double circuit. We're going to discuss all of them in this chapter. And this is the DC transmission line here. So this is a 500 kilovolt DC transmission line. You can see that only there are 2 line, one for positive, one for negative. And over here, 350 kilovolts line, that's a one positive, one negative, and also have a multi conductor for line. So in transmission line, you're carrying current. So, and if the transmission line is made out of conductor, has resistance by itself, and also it exhibits capacitance and inductance due to the two different things. Magnetic flux linkage will give you the inductance, and electric field due to the voltage difference between two lines will give you the capacitance. That's why you need to think about the inductance, capacitance, and the resistance of the transmission line. To model a transmission line for study, we need to know what is inductance, capacitance, and resistance of the line. Again, 99% lines are overhead. It's not possible to make underground transmission line because of technical and economical limitation on that, but we can make DC underground transmission line. And transmission line starts from 69 kV. If you have 69 kV or higher, those are called transmission line. If you have less than 69 kV, those are called distribution line. If you have a transmission line over 230 kV, that is basically a high voltage transmission line. Then you have 765 kV or higher, we call ultra high voltage transmission line. The conductor itself is stranded. You can see the different strands over here. This one particularly ACSR, aluminum conductor steel reinforced. That means conductor itself are aluminum, and in the middle there's reinforced is steel strands. So you have aluminum strand and steel strands. Steel is to reinforce it, that's not going to sag over the long distance. Then also have AAAC, all aluminum alloy conductor. So aluminum alloy conductor, all aluminum alloy conductor, aluminum reinforced. So there are different kinds of conductor out there. In the size, all conductor has a bird's name. We're gonna show you the name for the conductor in the class. We have a list of the conductors. Then there's a normal size for conductor is 1 milli is 3.001 inch. That means you have a 1 million C-mils. That means you have a 1 inch diameter of the conductor. If you have a 230 kV line or higher, and it go a little bit longer distance, you need to use more than one conductor per phase. Again, so resistance for DC is this over here. You have seen this equation before in as early as in ECE 100. So rho is the resistivity. Rho is your resistivity over here. Resistivity. That's a property of the conductor, and L is the length, A is the area. Based on that, you get the resistance of the conductor per unit length. You can do that per unit length. For AC resistance is a little bit higher than your DC resistance, usually 2% higher than your DC resistance, and also resistance could be impacted by the temperature over here. So this is the equation for that. T1 and T2, the temperature, and capital T is a constant, depend on the conductor type. And then R2 is a resistance at T2, and R1 is a resistance as T1. So you can see the impact of the temperature to the resistance of the conductor. We're going to do this problem in the class. That's all about the resistance. Now we're going to talk about the inductance in your tungsten line. What is the inductance? Inductance is basically total flux linkage over the current. So if you have a conductor over here, for example, is carrying the current I, and there's a flux linkage over here. So this total flux linkage is lambda. Right? So, and current I, then inductor of this conductor would be lambda over I. Right? So that is the equation for inductance. And how do you do that? Inductance, to find the inductance for a line, for a conductor, you have to consider both flux linkage inside the conductor, flux linkage outside the conductor. So Ampere's law give you the equation to find out the magnetic flux in magnetic field intensity. This is H is magnetic field intensity. All right. So if you find the H, from H you can find V, which is magnetic flux density. So you can find from H, you can find B, which B is magnetic flux density. From B, you can find phi, which is flux. Right? Then from flux, you can find lambda, which is total flux linkage. If you have more than one turn, that's what it is. So you have every turn will have the same flux, then you have multiply that by turn. So once you have that one, you can easily find L, which is lambda over I, right? So that's what it is. So you can do this for both inside the conductor and outside the conductor. This is the inside the conductor over here, and this is the outside the conductor over here. So you can do both, then you can add them to find total inductance for both. So to do that, let's go forward here. So again, so after doing all this derivation, this is the internal inductance, this is the external inductance for this particular conductor. Then if we add them together, internal, external for the conductor 1 here, then if we add them together, that's the equation here. So now this equation, I need to do a little bit of manipulation on that. So this 1 over 4 could be written as ln exponential 1 over 4. You know that ln E is 1 over 4 comes in the front. So it's so 1 over 4 ln E is same as 1 over 4. Then this one could be decomposed like that. So now you can now add these two, combine these two to make this one over here. All right. So this particular term here has a special meaning. I'm going to talk about that in next slide. So again, as I said, this term we call it R1 prime. That is basically we call it self-geometric mean of radius. So you have a cross section of radius R, then R time E exponential 1 over 4 is called self-geometric mean radius. We also call it ds. Right? So then this term over here in the previous slide, we have a term right here, R1 exponential and negative 1/4. That is basically replaced by R1 prime here. Okay. So now for the line 2, same thing. We replace that by what? R2 prime here. If you have a conductor, both conductors are same radius, then you can simplify that whole equation by just using R prime. right here. Again, your R prime is R exponential negative 1, 4, right? So then from here, if you go back from here to here, this is per meter. If you convert it to per kilometer, that is 0.2 factor in the from, then natural logarithm du by ds. Again, ds is same as R prime, all right? Again, we're going to do this problem in the class with this, using that equation over there. So now we're going to talk about flux linkage. So now I have two lines next to each other. This line will experience a flux linkage by current I1. So I1 is producing flux here, right? So and also I2 also producing flux here. Let me take a different color. So then I2 also producing flux here, right? So look at that. Each of the line has two different flux linkages. One is produced by current itself, and one is coming from the next one. So that one. So then you have two different flux linkages, like flux linkage for line 1 coming from current itself. You know that flux linkage is Li, right? So this is self linkage. There's the linkage due to the current in conductor 2, and same here. This is the self linkage, and this is the linkage coming from the current I1. So now, if we know that if we go back to the load and come back, so then I1 over here is basically negative I2, right? So if you do that, then this two equation becomes this. So that is can be replaced by simply I1 here and I2 here. So with that, now you also know that in your previous equation, we developed in the previous slide, this is the inductance for the line 1, and that's also in your equation over here. You also see that that is L11 negative L12, right? And for L2 is L22 negative L21. If I compare this equation with this equation over here, you can see that this is self inductance, that's basically right here, right? And this is your inductance due to the mutual inductance due to the other line, that is right here. So this is the mutual inductance part, this is the self inductance part. And similarly for the line 2, this is your self inductance for the line 2, this is the mutual inductance for the line 2, if you compare these two terms over here. So I11 we call it self inductance, and Lij will call it mutual inductance because it's coming from the other line. So imagine that you have three lines now. If you have three lines over here, right? So line 1, 1, 2, 3. So we'll take a different color here. Let's say this one. Let's say this one is basically this color. Let me take this off. I want to take three different colors here. So let's say this one is this color over here. That is 1. And this one is red over here. That is 2. And this is the other color. I just took this, the 3, right? So let's say that each of them producing their own flux and also linking the other two. So if I go over here, this one is producing flux, right? Every current produces flux. So that will be linking like that, right? So linking itself also linking 2 and 3. Then the other one, let's say red one, is also producing flux, and now it's linking like this, right? Then your yellow one also producing flux here, so it will be linking. So look at that. Each of the line producing a flux, that flux linking the line itself, also linking other two lines. That means, so here over here, this one will experience three flux linkage. One is L11 plus L21 plus L31. So that means flux coming from line 2, flux coming from line 3, and flux coming from itself, and so on for the other two lines also. So if you have a balanced system, if you have a multiple line, if you add all the currents for the line, you should get 0. We did it in the previous slides, previous lectures, if you remember that. So then if you have, let's say now, due to that, and also L equal to lambda over I, for the flux linkage for a particular line, let's say lambda I, the self one here, as I showed before, L I times I, then all other link is coming from all other line and their respective current, and J is not I because J I is right here. So if I now put in the equation over here, so this is the constant come in the front, then this is your self linkage over here, that is the mutual linkage over here. So this part is self, this is mutual coming from other line, right? So that is what your total flux linkage to any particular line. So now if I let's do I equal to 1 here. If I equal to 1 makes it over here, then L11 becomes this part over here, remember that, and this is your mutual one, only 2 lines here, and similarly L22 is right here, and this is the mutual part over here, all right? So let's try this for the 3 lines. You have 3 lines now, and you also know that in 3 lines, if you add all the current, it should be 0, right? So they're all symmetrical. That means they have the same line distance from each other. So lambda A flux linkage to the line A. I'm talking about this line over here. So I have 2 times 10 to the negative 7. There's a constant over here. Then IA, right? Then ln 1 over RA. Let's say all have the same radius, so I can take this one off here. Let's say R prime, all have the same radius, right? That's the self part. That's the self part. Then I have IB, so mutual part coming. So B from here, B to A linkage over here. So I have ln 1 over D, right? Then I have C to link over here. So I C ln 1 over D, D is the distance over here. So now also know that IB plus IC is 0. So the IB plus IC is negative IA, right? So over here, let's do one more line over here. So IA ln 1 over R prime, and I can take ln 1 over D out here. Then I have IB plus IC, right? Then if I come one more line over here, let me change the color. I like this color better. So, right? Then your IA over here, ln 1 over, sorry, R prime here. And this is negative A, right? So I can say negative IA ln 1 over D, right? So now if I combine it together, 2 10 to the negative 7, and IA can come out now. So if I put it together here now, ln, right, it's negative, so it's divided, so D is gonna go up over here, and R prime, right? And also I can say that this R prime is DS, we know that is self geometric mean. So that is be IA ln D over DS, right? So now to find the inductance, which is L, is LA, for example, over IA. If I do manipulation over here, it would be 2 times negative 7 ln D over DS. So that's your inductance for the line A. And as you know that there are same distance from each other over here, there's distance same, so they're symmetrical. For the symmetricity, because of symmetricity, your LA would be equal to LB, should be equal to LC, and that should be equal to 2 times negative 7 ln D over DS. Again, DS over here is R exponential negative 1 over 4. Right, so this is the equation for 3-phase symmetrical line, and it is same as single phase line. There is no difference. Same as single phase line. All right. So that's all for symmetric 3-phase line inductance. We're going to talk about a symmetrical line in the next class. After that, we're going to go into capacitance. So we're going to stop here for today. I'll see you in the class.